Previously, we learned how to identify acids and bases according to the Arrhenius definition and the Bronsted-Lowry definition. So in the Bronsted-Lowry definition, an acid was a proton donor and a base was a proton acceptor. These Arrhenius and Bronsted-Lowry definitions are really useful, particularly for aqueous solutions. But for non-aqueous solutions, so organic solvents or gas phase reactions, you can still have acids and bases, but we need a slightly different model to identify them. And that's the Lewis model. In the Lewis model, instead of focusing on H+, we're focusing on electron pairs. So what's interesting is that you can have an acid and a base that do not have hydrogen whatsoever. So instead, what we need to do is look at your electron pairs. So what you'll often need to do is draw that Lewis dot structure, right? So these are Lewis acids and bases. Not surprisingly, you'll have to look on that Lewis dot structure. So this right here sort of shows a comparison between the two models. When we look at an acid and a base, in Bronsted-Lowry, we were really focused on this H+, but in the Lewis model, what we're going to look for is a lone pair of electrons that something can donate. And that guy with the lone pair is going to be my base. This is really nice because it really broadens the definition of an acid or a base. Again, doesn't require H+, doesn't require water, anything like that. And what we really look for, or Lewis acids, are things that they either have an empty orbital or they're positively charged. In some way, they're able to accept electrons, whereas a base has a lone pair. Really, you're looking for a guy with a lone pair. He's your base. So let's look at a couple examples here. So first of all, we have BF3 and NH3+. So if we think about these Lewis structures, for BF3, it's going to look like that. And the fluorines all have full octets. I'm being a little sloppy here, but that's me drawing full octets on all the fluorines. And if we remember, boron was the exception. He likes an incomplete octet, so he just has these 3 bonds and then an extra empty orbital there. NH3, on the other hand, is going to look like this, and he has a lone pair on top. So again, focus on who's incomplete and who has a lone pair. NH3 here, he has my lone pair. He can donate them to this BF3 right here. So since NH3 is my lone pair donor, he's going to be my base. BF3 is my lone pair acceptor. He's going to be my acid. Nitrogen nearly always has a lone pair on it. 99.99% of the time, nitrogen has that lone pair, and he's often going to be your base. Notice we don't have conjugates necessarily. With Lewis acids and bases, they often just form a big complex, and you don't necessarily have any conjugates. So we're really just worried about the reactant molecules. Okay, second example. So CH3, NH2. So if we sketch this guy out, it's trying to give us some hints. So we have CH3 and then NH2. And again, nitrogen has this lone pair. And then we have water, like this. Now this one's a little tricky because we see that nitrogen has a lone pair, but then water also has lone pairs. So here we need to look at the products to get an extra hint. And we see that in the products, this guy, CH3NH2, gains a hydrogen. So he must hook onto that hydrogen right there. And the rest of this molecule, water, just sort of breaks off and floats away as OH-. So although water does have these lone pairs, he's not giving them to anyone, right? Nothing's touching those lone pairs, whereas the nitrogen's hooking on to this hydrogen right here. So this nitrogen with his lone pair, again, he's the donor, so he's going to be my base. Water, really, it's just the hydrogen, but it's some component of water that's accepting those hydrogens. That's accepting that lone pair. It's this hydrogen right here that breaks off. So since water, or part of water, is accepting that lone pair, water is going to be my acid.